Thank you, Mario. Good morning, everyone. Glad you're joining us this morning. I'm Joel Baker. I'm the director of the Puget Sound Institute at the University of Washington. And we're a group at PSI that are passionate about connecting the region's science community with policymakers and managers. And we do lots of that kinds of things in different contexts. But overall, our mantra is to show our work and to share our work. As good scientists and helping in our community, we like to provide venues where people can come in and talk about preliminary results, or I have a few crazy ideas. Let me get it out in front of a community to see what it's like. So, not that these are crazy ideas today, but they might be. So, take this as it is. It's a work in progress. It's meant to be a venue where we can, as scientists, talk about what we think is going on in the world. So we've been facilitating a series of workshops that focus on the science of Puget Sound water quality over the past couple of years. And we're glad that you're joining us for what is the eighth installment in this series. The prior workshops have examined various aspects of Puget Sound water quality, and I think many of you have participated in some or all of those. The topics of those are listed here. All of these are available on our website. All of the recordings, all the slide decks and everything from the prior workshops are available easily on our website. So we hope that you use that as a resource. We also intend to continue these. So you have ideas, suggestions for topics going forward, we'd be glad to hear from you on that as well. At our first workshop, Martha Sotula from Southern California shared her research into temperature-dependent oxygen supply and the demand that's informing how they're managing nutrients in the Southern California Bight. Today, we circle back on this topic, and we're fortunate to have Tim Essington and Stefano Mazzilli here to share their latest thinking on that topic. So with that, I'll turn it over to Tim.
Okay, thanks everyone for joining this call. I'm going to give a few opening remarks to just kind of give a little bit of context about me, kind of where I've sort of been fitting into this line of questioning. And then I'm going to quickly then sort of dive into kind of the conceptual framework that we've been using and how we've been trying to very systematically make a bunch of decisions about how we're going to address the problems of how can we evaluate the risk of low dissolved oxygen in Puget Sound. Just quickly about me, I'm a marine ecologist. I do a lot of work on marine food webs, and since I arrived in the Puget Sound area, the issue of low dissolved oxygen has always been an issue of interest to me. I've been involved in particularly Hood Canal related work for some time, looking at how species move in response to low oxygen, and whether or not there are any changes in food web linkages that happen due to basically predator and prey having different oxygen tolerances. So it's a topic I've been thinking an awful lot about. So in the context of the thing that we were talking about today is obviously a lot of the issues are about how to manage wastewater treatment in order to limit nutrients, with the goal being to protect the marine life. And it's that part that I'm at least have some capacity to speak to, is like, how do we address that question of like, what are the oxygen levels that are needed to support the species that we value in Puget Sound? So I'm going to see if I could advance this. There might be a bit of a delay. No. Try again. No. Oops. Should have seen that was going to happen. Okay, so big high level sort of conceptual frameworks from sort of physiology all the way through sort of risk assessment and ecology is, first of all, oxygen itself and low oxygen itself isn't itself an issue. It's an issue when the environmental oxygen levels drop below the thresholds that organisms need to do the things they need to do. So the example I always give is, while you're sitting in your room right now, there's probably plenty of oxygen right now. And if someone were to reduce oxygen by 5 or 10%, you probably wouldn't even notice it. Maybe if you really paid attention, you might notice maybe you're inhaling a little bit more often, but you probably wouldn't notice any difference at all. But if we somehow managed to transport your office and put it like halfway up Mount Everest, and we did that same thing of like, hey, now we're going to lower oxygen to 5 or 10%, Well, that's a really big, significant reduction in oxygen because you're much closer to your physiological thresholds. So I'm going to be talking an awful lot about like what are these thresholds? How do we come up with those thresholds? And then um, how do we relate the environmental oxygen levels to those thresholds? The second really key point is there are a lot of sort of endpoints you could consider on the spectrum of like what does oxygen do. The one that we're most upset about is the last one listed in the second bullet, this point here, dying. That's when all the adaptive responses are no longer available to an organism. That's by far the worst outcome. But a lot of things will happen to an organism before you get to that point. The biggest one is they generally tend to move. They tend to try to find parts of the water column that might move up and down, or they might move horizontally to try to find areas that have the oxygens they need that are above these thresholds. We do know that oxygens have, all organisms have a pretty good ability to acclimate to low oxygen. So they could change their blood oxygen carrying capacity. They could change their gill structure so they have a higher surface area. There's a bunch of things organisms can do. Then, of course, over generations, you could get local adaptation, which is not a thing we're going to be considering today. So this last point, I think, is a real critical one. It's the one that we're hoping to actually provide some guidance on is one, thresholds matter. And second, we want to ask, well, when and where are organisms present where the environmental conditions are dipping below those thresholds? So trying to look at not only the oxygen levels, but looking at the oxygen levels both in space and time relative to where these oxygen physiological thresholds are. And that's what we're try to speak to today. Okay, hopefully the next slide advances. There seems to be a delay that lasts long enough for me to click one more time. Here we go. One last piece of context that's really relevant in the context of climate change is that both physiological theory and tons of ample empirical observations let us know that these oxygen thresholds are themselves temperature dependent. So generally, as oxygen gets warmer, marine life needs more oxygen in the water in order to maintain their functions. This is just an example organism that's quasi-representative of something you might see where this axis here is the oxygen pressure. That's basically what is that threshold? What's that critical oxygen level that's needed to maintain life? If you're worrying about these units, a lot of physiological people who work on gas exchange like to work in pressure units, which is not my intuitive units. So these are in kilopascals, just so you know kind of where we're dealing with here. And this shows like, hey, you might get a doubling of where the threshold is from very, very chilly waters to very warm waters. And this is a very common temperature dependence that we see. Okay, so that's the context that we're sort of looking at. So one, thresholds, and then we're looking at how the oxygen levels relative to those thresholds vary in space and time. That's what we're going to try to address. So there's a lot of steps that are going to try to go into try to doing all of that. And the basic level, what we're really trying to look at is trying to look in space and time, what is the environmental oxygen partial pressure? And at the same time, for organisms that we're going to be using as our sort of our pilot cases, what are these critical oxygen levels and how do they depend on body size? And we want to identify both when and where does the oxygen partial pressure drop below the oxygen threshold. Doing this means we need to have a really structured approach to make a bunch of decisions. So on one hand, at a given location, even at a given depth, there's going to be variation in oxygen and pressure. So we need to make some choices like, well, what number do we use? There's also going to be variation with depth. So shallow water generally has higher oxygen than deeper water. And then how do we come up with these oxygen thresholds, given that not all organisms have been treated to the same robust laboratory studies? I think Stefano's probably going to talk a little bit more about the model that we're using. We're using the Salish model. Some of you may be pretty familiar with that. Just say it's a pretty complicated biophysical model that allows us, that's been pretty rigorously tested, that allows us to map the environmental oxygen partial pressure at various depths at a variety of locations throughout Puget Sound. And I'm going to just imagine a scenario. What if you just zoomed into one place in Puget Sound on a given day at a given moment. And if you could drop, say, a CTD in the water, you would see your typical profile of, say, PO2 and temperature as you go down with depth. PO2 is on your left, temperature on the right. So that's something we would see in sort of empirical observations. But because we're dealing with a model, we don't have these lovely lines. Instead, we have a bunch of points where we have 10 different layers that represent different chunks of the water column at each location at this particular moment in time. Now, over the course of the day, we don't just have a single observation, but we have a different observation for every hour of that day. So now for every layer, we've got a bunch of different PO2 measurements and a bunch of different temperature measurements. So this is where we need to now make some choices like, well, when we're thinking about what is the PO2 and what's the temperature, what number do we use? Because there's more than one for any given day. So what we're doing in this first round is trying to make a simple and what we think is a conservative approach. So for each layer, so say right here, we've got a bunch of different PO2 measurements, and those all represent different hours of the day. We're going to assign to that layer what was the smallest PO2 we saw in the course of a day. And that's the number we'll assign to that, and we'll be calling that just the min PO2. And then we go to this layer, do the same thing. What was the smallest number? It's that. What's the smallest number? We use that. So now we're going to be looking at just what was the minimum PO2 over the course of the day for each layer. And that's the thing we're going to be looking at when we're comparing it to the oxygen thresholds. For temperature, rather than use the min temperature, we're just going to use the average temperature throughout the day. Again, that's more of just a simplifying assumption. So here we have our mean temp throughout the day. Okay, so that's how we're kind of treating all this very robust and rich model output from the Salish Sea model. Now, how do we come up with these thresholds? So I've mentioned that there are these environmental thresholds, and they're often called P-crit, or stands for critical oxygen pressure. I've been working on summarizing every study I can find where someone has taken an organism and done a particular type of laboratory study to try to define, figure out where are these thresholds. The data set that I've used has over 150 species, over 450 laboratory measurements, and these things span 6 different phyla, so it's pretty taxonomically broad. In a previous project, I developed a computational approach that allows us to estimate the critical oxygen threshold for any organism based on, first, its taxonomy, so what's literally the genus species, the temperature, because it's temperature dependent, also body size, because there is a small effect of body size. But then lastly, every laboratory has like a slightly different way that they did it. So I basically have a way to account for the fact that some laboratories measured the critical threshold this way, and some people measured it that way. So I'm trying to count for as many things that we can possible. So overall, then I can come up with a given species and say, like, this is my best estimate of the critical oxygen threshold. And I can even tell you something about the uncertainty in that number. So we'll be showing you a little bit of that uncertainty later on. So just quickly, what you can see, this is just a bunch of made up organisms showing what this critical oxygen partial pressure might look like. And here on the bottom, some hypothetical taxa that are well within the realm of what we see, where we see some taxa, as you know, are just super tolerant. They can have really, really low thresholds, which means they can tolerate really, really low oxygen levels without them being really, really stressed. Also, you can get some taxa that have a really, really strong temperature sensitivity. So in other words, their threshold increases rapidly with temperature, where others are much flatter. So we're able to see all that richness of taxonomic diversity, and that's kind of baked into a lot of the things that we're going to be presenting. And then lastly is when people measure this threshold, it matters like what threshold you're talking about, because it's the threshold in order to do what. So on one hand, on the left-hand side of the screen, some people measure the threshold in terms of like, what's the minimum oxygen needed just to keep this poor little fish alive? So that's a pretty low bar. And then alternatively, some people measure it like, no, I'm not interested in that. I'm interested in, there's a bunch of things an organism needs to do just to do minimum functions and sort of routine activity. I'm going to sort of benchmark my my oxygen threshold is, what's the oxygen threshold in order to meet that higher bar? So we're going to be only today presenting the second one, but just know we have all the analysis you've seen today. We've also done for the sort of the very, very dire sort of endpoint. Okay, so taking that same graphic before, here's our model. Here's the model. We can simplify that in terms of the min PO2. We simplify that in terms of the min temp. Based on the min temp, or the mean temperature, I can then calculate the P crit that I think that organism would face if they were in that layer. So kind of it's high here and it goes down, 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 just like that. So that is an organism specific or a species specific estimate that's based on the environmental temperature and also the body size of the organism. So just want to see what slide's coming up here. Well, maybe I'll be surprised with all of you. Just go ahead. So here's just an example of taking that one point in time and looking at just one particular depth. And what we're going to do is in the line that's super squiggly that's the environmental PO2 over the course of the year, starting in January, very high in April and May, comes down, it gets low. This is in sort of mid-December, and then it comes back up. So these are bottom layer PO2 measurements. So that's the environmental signal that we're looking at. And then this little dotted line on the bottom is what would be the oxygen threshold for this routine moving around for a Dungeness crab if it was living on the bottom. And it looks super flat just because the scale is so big, but it is going up and down because the temperature is changing. It just doesn't change nearly as much as this environmental signal is going. And the key thing in all this is you probably paid attention right about here. That's a point where we flipped over, whereby the environmental oxygen is less than the threshold. So that's the thing we want to be paying attention to, is when and where are places where the environmental oxygen has dipped below the threshold. Now, one last flourish here is we could show you those plots for a gajillion places, but then we'd have to show you 2 lines for everything, and it gets kind of confusing. So instead of just showing both the min PO2 and the P crit, instead what we're going to be showing you going forward is the ratio of those two. So for each layer, what we do is we take what was the actual PO2 and we divide that by the P crit, and then we're going to get this number that looks like this. The actual numbers don't really matter. And that's just the ratio. What was the environmental oxygen relative to the threshold? So a value of 1 means that we are exactly at the threshold. Numbers greater than 1, meaning the environmental oxygen was greater than the threshold, and values less than 1 means we drop below the threshold. So going forward, we'll be showing that ratio in all the plots. So here's that same graph I showed you before, but instead showing you as that ratio. It's the ratio of what was the environmental oxygen relative to P crit. It basically shows the same thing, blah, 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 blah. Boom. Here now we drop below the threshold, and then it came back up. Okay, one last thing before I hand it off to Stefano is here I've only been showing you single lines as if we knew the P crit perfectly, but we don't know the P crit perfectly. Laboratory studies, they still have some uncertainty in the numbers. And sometimes what we're doing is we're using information from a related species to say something about it, the species we care about. And that also introduces imprecision in our estimates of what the P crit is. So another way we can look at the same graph is add in uncertainty bars, a confidence interval, and that ratio of PO2 to P crit. And all of that uncertainty, the error bar, is due to the uncertainty in what that P crit, that physiological threshold actually is. So that shows you on this particular graph, this is our best estimate in the line here. And then the gray bar is like the lower bound of what we think is plausible. And then you see the lower bound of that crosses the threshold obviously a lot more frequently than our best estimate. Okay, with that, I think I'm going to hand it over to Stefano. Is that right, Stefano?
Yes, that's correct. Thanks.
All right,
Thanks,
I'm going to give you control back.
Let me see if I can. Okay. Fantastic. Thanks, Tim. That was a great explanation and much needed with some of the complexity here. So I'd like to continue with the methods a little. First, I'll just say my name's Stefano Mazzilli. I'm from Puget Sound Institute, and my focus is on biogeochemical changes and modeling and monitoring of that in Puget Sound. And here I'd like to dig into some of the details of how we've been using the Salish Sea model in this initial investigation, and then follow that with some of the initial results for some of these species. So we are in a great position to start this work, as there's been a big push in Washington State in recent years to improve not only the monitoring, but also modeling of physical and biogeochemical change in Puget Sound. And it gives this fantastic opportunity to work with folks like Tim and others that are really looking at this understanding of how these changes might, what these changes might mean to marine life. So in this initial application, we're applying this threshold that Tim talked about between the environmental oxygen and the PCRIT, or the metabolic index approach, as it's being called, to Salish Sea model outputs and the generated data from that. So we use those Salish Sea model outputs to calculate available oxygen levels, quantifying spatially how an organism's available aerobic habitat might change for a particular place in time. So just a little bit of background on the model as a reminder for many here. The Salish Sea model is a finite element model. It's usually run and has been run for several years, which includes 2014, which our analysis is focused on. On the right here, you can see the area coverage at 16,000 cells or nodes to this finite element model, and it covers a much broader area than Puget Sound, shown here where my cursor is. So at each of these cells, there are 10 depth layers shown in the schematic on the left, and parameters such as oxygen, temperature, and salinity that we're using as inputs and that Tim has talked about, generally saved hourly. And so we're using that hourly input as a starting point. We're using this to consider the existing condition scenario for 2014, and that is the model data set from the Salish Sea model that's virtually identical to that's been used by the state and published in Ahmed et al. 2021. So this is really the first application of this approach of applying a metabolic index to model scenario results in Puget Sound, and it can be applied and adapted to other scenarios and models such as live ocean to examine issues key to management impacts on species with change in climate and nutrients. So for this initial approach, we have 3 species. Today we'll be showing the results for Chinook and Dungeness, and can provide links to results for all of these in the workshop follow-up. While it's not as economically important, English sole is often monitored for toxics, including Puget Sound Partnership and vital signs. And Chinook is a really good, if a little bit difficult, example as we've gone through it, to start with for salmon, particularly as some of the Chinook stay in Puget Sound year-round. Different species occupy different depths. And although we're not considering all the factors that could constrain habitat, we have focused on the depth-specific outputs of the model that Tim talked about earlier, because of the importance and influence on the predictions that are made with a metabolic index approach, and therefore the available habitat or aerobic habitat that an organism has. So when considering available aerobic habitat to salmon, we look at these prediction results using the model outputs for each layer of the water column to a maximum depth of 100 meters for the salmon. So looking at each of these outputs. For crab and sole, things are a little simpler. For crab, we examine results only in the areas to a depth that is less than 80 meters. And then we just look at the bottom layer as a potential aerobic habitat for those species. Similar approaches are used for sole, using an area of a depth less than 100 meters. So moving on to some of the results. Let's look first at the Dungeness crab. And the next few plots show results at different locations within the sound. This plot shows the estimated metabolic index, so that ratio for the bottom waters at the site to the seaward side of the Pen Cove Inlet. And this is actually, we pick sites that are actually located alongside Orca buoy measure data, but what we're showing today is the model data from the Salish Sea. On the x-axis here, we have the time through the year in days for the year 2014, and on the y-axis, we have the routine index result at that location. So the way to interpret this change in metabolic index is that at this particular location, the index approaches but never crosses this critical threshold that Tim was talking about earlier. So if we think of a crab living in this location, it should be able to maintain routine metabolic capacity throughout the year. Just a reminder that routine metabolic index is calculated using those parameters that support the basal or survival level functions, but also routine movement and activity, for example, feeding and transport. Another important point here when we look at these plots are that as at this point of 1, the available oxygen falls below the critical threshold for that particular species in that particular location. This is the ratio of pCrit to PO2 that Tim explained earlier. The lower the index result, the greater the risk approaching this line. Now moving to a location where we know there's seasonal hypoxia, here in Southern Hook Canal, shown here up on the right-hand corner. This has a steeper decline in the summer and late autumn, approaching 1. And this threshold is passed for oxygen for a short period of time in late October, indicating for crabs at this location, we would have a higher likelihood of impact to these routine activities when we're looking at the bottom level waters. And this is around a depth of 45 meters, this particular location, at least in terms of the model result. This is an animation. I might just have to get it started. That's great. This is an animated map showing the same daily data, but across the sound. Areas that will show up in red are less than 1 in the summer and autumn months. Areas that show up in orange are where this metabolic index is approaching, but has not reached this critical threshold of 1. So the first occurrences of this are going to occur in Hood Canal in the south, and in Bellingham Bay in late August. And in the northern regions, some areas of Pen Cove here, as well as Bellingham Bay, have sequential days below the critical threshold. Sequential days of impact are really important in terms of accumulated risk and opportunities for recovery. In the south, the southern end of Hood Canal persists until early November, then returning to the baseline by the end of the year. Showing these model estimates in a different way to focus on areas where environmental change in oxygen concentration fall below the threshold levels, we can make observations on the different spatial extent and duration. Noting here that since this is the bottom level predictions of the metabolic index for Dungeness, the hashed areas here fall outside of the relevant depth habitat. So we're really looking at areas less than 80 meters that are not shaded out. First, spatially, the areas throughout the year that fall below 1, at least one day, are highlighted, showing some of those areas that were identified earlier in the animation. Bellingham Bay in the north, Pen Cove and Hood Canal. Second, we can start to get a bit of a nuance in that in terms of the total duration or days that occur within a year, coloured here to show the number of days. What we have is a total of a week to a month for cells in blue, in Bellingham and Pen Cove in this lighter blue, extending to multiple months in the landwardmost reaches of Hood Canal, shown in pink here for 3 to 4 months binning. Lastly, on Dungeness crab, here we're using the same approach, but to show something a little bit more complex, which is the number of days per year, but illustrating an example where we can subtract one scenario from another, and a way to possibly show change in days between those two scenarios from model results. So this helps us understand the impacts of aerobic habitat compression or shrinkage in actual number of days. Here, we're simply showing the impact of comparing the existing to reference scenario, where the reference scenario has the removal of human sources of nitrogen loading, noting that all other conditions are kept constant between the two scenarios, which includes temperature and climate. That's quite important. So this really focuses on a sensitivity in terms of the influence of nutrients. So by calculating the metabolic index for each of these two and then subtracting one from the other, we see the change in days here on the right. And we see that these changes in days show a less than 7 days, the lightest blue, for example, for Bellingham and parts of Hood Canal, to what's binned as between 7 and 30 days for parts of Pen Cove and the most landward tip of Hood Canal. So these indicate areas where aerobic habitat may be compressed by those influencing factors. Okay, now moving to the more complex case for salmon. Unlike adult crab, where we should just take the model outputs for aerobic habitat representing the bottom layers of Puget Sound, for salmon, we need to consider parts of the water column that they may move through. So looking at predictions down the water column, first, as expected, on the surface layer, we have constant gas exchange, and the resulting baseline metabolic index, or that ratio, for winter remains fairly constant and never approaches 1. And once again, we're looking in Hood Canal here. If we look at a situation where a fish swim into the bottom of Hood Canal at this location, which we know has seasonal hypoxia, then similar to what crabs experience, the model predicts they would be exposed for a short period of time with a high likelihood of impact on their routine activities if they don't choose to swim to a higher level of the water column during that period. So these layer differences are really interesting for pelagic species like salmon that can move through the water column. Here's another example where we're taking the average of the water column, which may be at the moment the best representation we have currently of what a mobile species might experience as we compare different areas. So looking at this spatially for salmon, as we expect, if we look at the average water column result throughout the sound, as expected, we get no days showing results throughout because there are no days that are below that threshold of 1. The work on salmon highlights the importance of efforts in Puget Sound on how to interpret the results of habitat change in risk, and for our next step in the work to consider options on how to aggregate data on habitat condition that represents where salmon or other species are impacted. Next steps are volumetric analysis for these subregions to kind of tease that out, and really are looking forward and appreciate feedback and suggestions on how to assess risk, and particularly for these mobile species. So in summary, looking back through the work that's been presented, there's been a clear theoretical and scientific foundation available to support, which is being supported by growing experimental evidence to determine how much oxygen is required by species in Puget Sound. Existing Puget Sound water quality models provide the things we need, the dissolved oxygen, temperature, salinity, and depth pressure data, and they are available in measured data, as Tim and others have been using earlier, to calculate the oxygen available for a species at a particular place and time. We've demonstrated here that it is feasible to determine oxygen requirements and consider species-specific habitats for water quality assessment. And the initial analysis results confirm that dissolved oxygen impacts occur for those species, and they're limited to certain areas of Puget Sound and periods of the years identified. In the next steps, we're looking to analyse in future the different life stages and sexes, expanding on additional species, and this work is being particularly led by Tim in conjunction with his new student, Veronica Lee, who should be on this call and will be doing a PhD on this particular part of the work. We're looking to refine the metrics and look at the habitat volume, and most importantly now, be able to apply this to consider future change, and particularly temperature and its influences. And with that, I think I'm going to hand over to Marielle.
Yeah, so we have a lot of kind of input as we think about these next steps that we'd love to get your thoughts on. But before that, we'd love to hear any questions on kind of the method side of things or on these preliminary results. So feel free to raise your hand and we'll unmute you, or you're also welcome to drop questions into the chat. Maybe while folks are thinking, what I will also do is in this theme of expanding to additional species, we know that the benthic side is a really important consideration. We've had some conversations with experts in the region about what those next species for the benthic side might be, but also would appreciate everyone here's thoughts on what those could be. So if you work with benthic species and have a strong opinion about kind of which one we should prioritize next, please feel free to add that to the poll that I just opened up. If you're like, I don't know benthic species at all, hold tight, that's okay. I've been learning a lot more about them in our conversations as well. While folks are filling that out, I don't see any raised hands, but Joel or Tim, just anything you want to add in terms of kind of reflections on what we've been seeing thus far?
I have a question for Tim, if that's fair. Can I do
Yeah, go for it.
So thanks for the presentation as always. And I understand the P-crit is a single number for a species at a given body size and temperature. Great, but there's that transition zone where the fish or the organism begins to get impacted by lower dissolved oxygen, right? Changing its behavior, it's changing swimming speed and things like that. How do you incorporate that into, maybe not this model, but how do you think about that? So I'm not, there's enough dissolved oxygen to survive, but I'm not super happy, so I'm going to change my behavior. How does that work?
Yeah. Try not to have a flippant answer that says spend millions of dollars and you figure that out for every species. Yeah, I think, I mean, I don't think I possibly have a satisfactory answer to that. But I think the question really nicely illustrates a core limitation of how do we go from a laboratory experiment to what matters in the field. And the nice thing about a lab, it's nice and controlled, and you can measure things a certain way, and you can define a particular endpoint, which is this routine metabolism. And then a bunch of things change once you go into the real world. On one hand, you could argue that these lab measurements are there's a higher threshold because organisms need to do a lot more than what they're just doing when they're moving around in a lab.
Right.
I think that's a very sensible argument. On the other hand, the lab experiments are also kind of contrived, where you're taking an organism that was very happy, and all of a sudden you went, and now the oxygen is terrible, and you don't allow for that acclimation response.
Mhm.
So in that way, you would actually tend to see it the other direction. So I think a sensible approach is this just provides a benchmark, but it should always be viewed through the lens of this is just a measure of relative risk. So the literal number doesn't matter. It's about like what are our risk tolerances for this question, and that's how I've been formulating it.
Great, thanks.
Appreciate that, Tim. Alan, go right ahead.
Okay. Just a question. Using the Salish Sea model, and I'm not overly familiar with how it's adjusted to account for different years than the base model, knowing that 214 was a heat dome year, and how much of the changes in the DO temperature are related to the either estuarine exchange or ocean inputs. And I'm just familiar with the Bellingham Bay issue, which indicates that most of that change by box model projections seems to be coming from outside the area. And the whole question of this is, what is the relativity of this to the local nutrient outputs from the watersheds?
I can have a go at that, Marielle, if you like.
Sounds great.
Yeah, thanks, Alan. I think that's a great question. It's getting more to how representative is the biogeochemical model outputs for the Salish Sea model. I think we can have a conversation offline on this, and there's been a lot of a lot of discussion. But in summary, the 2014 conditions are forced by the ocean boundary data that's modeled. It's modeled data, so that's limited in itself on the ocean boundary. And they are, as you discussed, the main driving force in terms of a particular year. So we can drop in the chat Turang's paper where he looked at change over time during the heat wave, and that'll explain a little bit about how that shows that influence. But I will point out, since you're looking at Bellingham Bay, the model is limited when it's looking at riverine inputs on that, particularly not just on temperature, but also nutrients and so forth. And that's the fact that until now, we're having to use regressions from loads in the catchment. In future, these are planned to have measured gauges that ecology has put in place, but at the moment, it's a regression from some limited data sets and played across different rivers.
Great, thank you. I'm just gonna, before we go to Aiden, highlight some of the discussion in the chat and the great recommendations there about particularly the idea to look at a theoretical, if we raised water temperatures by 1 degree, how that would affect the PCRIT, and just thinking about that as a first step towards kind of current and future temperature changes. And that is definitely feasible. And so appreciate that recommendation. Aiden, you're up.
Sweet. Yeah, just first off, thank you guys for your presentation. That was really interesting and such a cool application of the Salish Sea model. So awesome. My question is maybe for Stefano specifically. I'm curious if you can reiterate or go into a little bit more detail about how you guys have thought about or maybe applied quantifying the impact of kind of successive days of low oxygen and the cumulative risk of that stressor without time for recovery. I'm working on a project studying the environmental impacts on bull kelp, and we're really interested in similar impacts of temperature and how we can kind of quantify that. So.
Thanks, Aiden. Well, that's what we're on this call for. We're trying to get the ideas from you guys, right? But no, that's actually the whole point of the project is that we really have this ability for this granularity, and it's obviously important for the work that you're doing as well. And it really matters. The aggregation matters. And so those plots that I showed, we do now have the days, because we're dealing with a threshold, we can, and it's a threshold that's actually relevant to the organisms, we can actually start to quantify that. And so looking at the number of days of exceedance, the exposure time and return time are things that we've been looking at. Yeah, but love to have your thoughts on that or others, and please do get in contact because we're at a point where we can tweak those to make them more relevant to organisms.
And Tim, do you want to maybe talk a little bit about just kind of what's known, like the differences in what's known around dissolved oxygen duration tolerances versus when we kind of look at the metabolic index side? Because there's what can we pull out from the model, and then there's also our confidence in what does that mean?
Yeah, I think that's a really good question. Yeah, I mean, it really gets to like what we don't know, like what, let's say a Dungeness crab cares about. Does it care about an hour of bad exposure? Does it care about a 3-day exposure? I imagine for sure the latter, the first one, I don't know. Given that it has all these other sort of responses it can do in the short term. So, you know, we do know that the duration of exposure and the intensity of exposure both matter. Where you draw a line and say like this is bad and this is not bad, I really don't know. And that's, I think, part of the reason why we just chose a really simple thing and just say like, hey, if it ever dropped below at any point in the day, we're going to count that as bad. But perhaps there's a better way to address that, and I'm wide open to other ways of addressing that.
Appreciate that, Tim. And I think that's where we can certainly share, here's what we see as data points, and then that creates space and context for conversations about what those different risk tolerance are in different applications. Okay, I'm going to go ahead and close the poll on the benthic side. Really appreciate the feedback that we're getting there in terms of what some of those priorities are, and welcome if folks have strong feelings on the why or cautionary tales, please feel free to reach out and email me and we can move that forward in our subsequent analysis. All right. Tim, this is a question for you just around the relative sensitivity of the 3 species that we selected and kind of the thought process there about the different habitats they are in, but also that sensitivity.
Yeah, the 3 that actually we only showed 2, but we've done the work on 3. They weren't hugely different from each other. I mean, I'd say of the 3, salmon had a higher level for their thresholds. In other words, they need more oxygen than crab, and I think sole were kind of in the middle. I think someone else, like in the grand scheme of things, where these animals fall out, and they're pretty ordinary in that broad meta-analysis. They're not particularly tolerant and not particularly sensitive either. Yeah, so they kind of fall in the middle. I would say the differences between the taxa, I think, are probably real, but they're starting to push the limits of our precision of trying to estimate them in the first place. I don't know if I fully answered your question, Mario.
No, I think that does kind of contextualize the 3. And certainly, again, our next step is to expand species. And so if folks go, ooh, I think this particular species is really important ecologically, environmentally, culturally, or I think it is sensitive, I would love to see that. Beyond just benthic species, we would really welcome those sorts of inputs. The nice thing is, in having ramped up a lot of the infrastructure here, now adding on gets simpler. There's also a question, Tim, for you about just kind of the benefit of using partial pressure over a DO saturation.
Yeah, I think I just tried to answer that as well. Yeah, and that really just comes from physiologists that work on gas exchange like to use partial pressure because it makes sense in terms of what they're doing. And we have to pick a unit, and we picked a unit that's sort of most aligned with laboratory studies. We could easily turn everything back into milligrams per liter or percent saturation, or pick your favorite unit. Yeah, so we could easily present it in any way. But in terms of the organ's physiology, it is partial pressure is the thing that really matters.
And along those lines, there's a question from someone who joined a little later, just about temperature sensitivities for different life stages. And so
Yeah.
at this point, this initial analysis does not, but especially in the context of crab, I feel like that was something that came up where like that we expect there will be really differences there as we look at life stages. And so look forward to doing more of that. Tim, anything you want to add?
Yeah, I mean, other than I think the life stage question, I think is a really important one. What we can tell from sort of the body of work on that is very, very early stages tend to have they tend to be more sensitive to oxygen. Um, uh, for the reasons you might expect, they're small, they have a very funky surface area to body mass ratio, and they may not have developed enough of their oxygen regulatory capacity. But then once they get to a certain size, and I don't know what that certain size is, it's gonna be different. At that point, everything really seems to be driven just by body size. So it would be nice in a perfect world where we could say for Dungeness crab have a like a megalope specific number. The good news is we do have a fair number of experiments on crab megalope, so we could try to come up with something on that, and that's something that I think would be worth looking at.
Wonderful. And I'm seeing also some suggestions in the chat in terms of, again, additional analysis, in particular, just the heat wave metrics for methods to characterize the duration and intensity of low DO waves without knowing more than peak for a given species. And so appreciate that recommendation, Caitlin. Again, other questions, suggestions, feel free to raise hand or drop them in. You know, there's a lot of different ways to slice and dice this information, and mostly we want to be able to provide context. And so, for example, we'd really appreciate thoughts if folks have it on salmon and kind of these more mobile species about how to think about that depth. Does the water column average within that top 100 meters that we've done thus far make sense? Or would folks like to see that particular species analyzed in a different way? I'm gonna let folks continue to noodle on that while we go to this other question here in the chat. Or comment about just that it would be great to do a comparison of human population increase relative to the loss of marine oxygenation producing life to the loss of dissolved oxygen, particularly when thinking about roadway stormwater runoff and the decaying matter there. So thank you for that recommendation.
Mario, if we have a minute, since I screwed it up, could you go back and show the Dakota slide, which I meant to mention at the setting this thing up? Is that possible?
Yeah.
Because there's been some really nice work done recently from a graduate student at the University of Washington. I think was presented in this forum a couple of times ago, but took a really hard look at all available data of what we know about the dissolved oxygen concentrations, the time series of that, like how it's changed over time. And it's a great question, but the perception is that there's been changes, and there has been. So this graph you're looking at here is from Dakota Mascarenas. Who's on? I let her talk. Dakota, take it away.
Oh my, you're putting her on the spot.
Our students are really good, and they can take it on the fly. Or Dakota, or I can mangle it for you. I'll do it. This is she looked at the rate of change in dissolved oxygen over time, and these are the results of that after a lot of work of filtering the data and cleansing the data and things by area in Puget Sound. And you can see the rate of there are 3 of the 5 areas that she examined where there has been a decline in the rate of oxygen on the scale of less than 1 milligram per 100 years. So there has been a significant but small rate of decline of dissolved oxygen in the waters of Puget Sound. The interesting part of that is, if you click on to the next slide, about half of that decline is due to the warming of the water itself. So just that process that Stefano was speaking of, that as you warm the water, it's less soluble. The oxygen is less soluble. So about half of the change we're seeing is due to the warming of the water. Mapped on this over this 100-year period, of course, there's been a fairly large increase in the population in the watershed. So presumably the loadings of things have increased over that time. So that's the historical context of dissolved oxygen in Puget Sound. And thanks again to Dakota for doing all the hard work.
Agreed. Really helpful to see, and impressive the amount of data and thoughtfulness that went into that. We've got another question in the chat, just about temperature or DO monitoring at the marine freshwater interface in deltas. Just knowing that adult salmon will kind of hold in cold, deep marine water during warmer periods before entering a spawning stream. And some of that's probably osmoregulation, but interesting to look at temp and DO trends. Tim, do you want to take that one?
Yeah, that's a great idea. And I think that speaks to the sort of the broader question that we kind of have on here is trying to, we can do the thing like, hey, we're just looking at all the spaces, but it would be really good to know some of the key sort of life history bits of like, oh yeah, when they're in this spot, they're always at these deeper depths when they're here, and we should be paying attention to those. So I think that's the level of granularity that I think would be great if this project can sort of get to, is sort of via expert opinion. And that's a lot of what Mariel's been doing behind the scenes, is talking to a lot of people and like, hey, where is that organism at what time of year, that kind of stuff. So I think that type of thing, I hope that we can continue, not just for salmon, but for all the species we want to look at.
Great. Appreciate that, Tim. We've got another question about just studies of DO on any areas of discharge into Puget Sound, which, yes, there have been really extensive studies, and we can definitely share out some of those links and reports. Department of Ecology in particular has led a lot of modeling with the Salish Sea model, looking at that, as well as Terang Kangankar. So happy to share those resources for folks who may not have been living and breathing the world of nutrients for the last couple of years, like some of us here. Other questions or suggestions? And certainly, you know, if you have shower thoughts as this is all soaking in the coming weeks, and go, I want to brainstorm if that's possible, or I think it'd be really interesting if you looked at XYZ. Again, please do not hesitate to reach out there. All right. It is very possible that we are hitting a point of diminishing returns in terms of questions and ideas, which is a-okay. We scheduled 2 hours, just really wanting to make sure we had more than enough time, because I don't know, sometimes it feels like we get to the end and are just getting into meaty discussion and have to wrap up. But I'm gonna wait for another 30 seconds in case anyone has a light bulb moment. All righty. Joel, any final closing thoughts that you want to leave us with today?
I would just like to thank you for organizing, as usual, Marielle. Excellent job, and to our speakers. And I also like to thank all of our collaborators in this space. There's no time to give everyone credit, but I'll try. So, you know, Trang's group at the Pacific Northwest National Lab, the Ecology Group, people who have shared model results, shared discussions, fantastic. Our work has been sponsored by King County. It's been sponsored by EPA. It's been sponsored by the state agencies. So I think it's a real team effort, and you're seeing a slice of it this way. But this is certainly part of a larger program, and I hope you stay enrolled. I hope we'll be doing more of these webinars and other venues down the road. So thanks to everyone.